Section 21, optimization. Optimization problems are just like the minimum and maximum problems that you did in the increasing and decreasing section, where we're finding relative maximums or minimums, except the difference is that you have to set up the equation based on geometry or real life situations with like money costs for building things or fence size. So creating, like doing the algebra to create the situation where you want to take the derivative is the hard part. After you have the equation down to two variables and you take the derivative and you set one of them equal to zero and then you figure out the critical points and you test to see which one is what you're looking for. That's basically exactly the same as quiz section 16. So it's just a matter of setting it up, doing the pre-calc problem that comes in before. So let's look at a few problems. First problem is the box one that was on my website. I'm going to zoom in on this guy. So a manufacturer wants to design an open box having a square base. So open box means this is not a face. That's like a hole there. And an outside surface area of 10 square inches. What dimensions will produce a box with the maximum volume? So, we need to figure out the equations we need to use here. And when you have something that's a geometric situation like this, that's in 3 dimensions, you should immediately think I have surface area and I have volume as my equations. So the surface area of a box is, well, I only have 5 sides here because I'm not using the top one. So it's going to be 5 times, so it's telling me that the width is the same here, but the height could be something different. So actually I don't have 5 sides that are all the same. The bottom is width squared because it's width times width, but each of these are width heights. So I have actually width squared plus 4 width heights. So not as easy as it looked initially. Okay, volume equation is actually as easy. It's just width times height, so width squared heights. Alright, now we know the surface area equation, or what it should be equal to, because we know the surface area should be 10 square inches. So 10 is equal to width squared plus 4 width each. Okay, so now our goal is to solve for a variable in this equation. There's a obvious easier one to solve for. W would be really hard to solve for because we have a W squared, so we should definitely solve for H. 10 minus W squared equals 4WH. Divide both sides by 4W. And you get H is equal to 10 minus W squared over 4W. It's not too bad. And we're just plugging it in for H in this equation because we're trying to maximize the volume, so this is the equation we're going to end up taking the derivative of. That will always be true. Whatever you're trying to maximize, that equation is what you're going to be taking the derivative of. And then you look for dv, d whatever, and set that equal to 0, and that'll help you find the maximum. So anyways, let's plug in 10 minus W squared over 4W in for H here. I should probably simplify this because I don't need to use the quotient rule, so I should take advantage of that. This W on the bottom can kill that squared so that it's just W times that stuff, which is nice. So I get V is equal to 10W minus W cubed over 4. And I can take the derivative now. This is just a fourth out in front of this whole thing. So when I write the derivative, I'm just going to write this as a fourth out in front like that. times 10 minus 3w squared. Oh, and a slight mistake. dv dt is not what we have. When we took the derivative, I took it with respect to w, because I want to find the rate that the volume's changing with respect to w and maximize that. So now I just set that equal to 0. And so I get 0 is equal to my equation, 1/4 times 10 minus 3w squared. And now I just got to solve for w. So I'm going to distribute the 1/4 in, and I get 2.5 minus 3/4 w squared. Add the 3/4 w squared to the other side. 3/4 w squared equals 2.5. And then I multiply by 4 and divide by 3. Multiply by 4, I get 10. Divide by 3, I get 3 1/3. That equals w squared. And so w is equal to the square root of 3 1/3. Which seems horrible. Well, okay, real quick, before I talk about that, the reason I totally ignored the negative root 3 1/3 is because you don't have a negative width. It's a positive width. So I'm just going to completely ignore that. I'm just going to keep the positive number. But yeah, the reason this isn't that bad is I already have the width. That's the answer to part of it. I just need to figure out the height now. So I need to figure out, or plug this root 3 1/3 into my equation where I'm solving for height, which is this equation. And so I get h is equal to 10 minus root 3 1/3. Well, actually, root 3 1/3 squared is just 3 1/3, so it's 10 minus 3 1/3. Well, that's easier. Over 4 root 3 1/3. And on a quiz, that would be an acceptable way to leave your answer. So we'll just box those guys up. One thing I forgot, units, inches for each of these, because inches are in the problem, square inches for the area. And that's one related rates problem. So these are pretty hairy. There's a lot of algebra here. But all of this algebra and the stuff here, none of that's calculus. The actual calculus step was really easy, this derivative. It's the word problem part that's hard here. All right, on to the next problem. Okay, we need to enclose a field with a rectangular fence. We have 500 feet of fencing material, and a building is one side of the field. So we don't need any fencing on that side because a building's there. Determine the dimensions of the field that will enclose the largest area. So, okay, we have a building. And it doesn't tell us how long the building is. It tells us it's just a side. So I assume this building can be anywhere from like a foot wide or an inch wide or something to 500 feet wide, our maximum fence length or whatever. So we know we have some sort of fence coming out here like that. And we want to enclose the largest area. So it's a rectangular fence. So we have a width, or two widths, one on each side, and we have a length. And we don't need to worry about the side because we don't need to use our fencing on it because there's a building there. So just like the one above, we're going to have an area formula, and we're going to have, in this case, a perimeter formula because we know we have 500 feet of fence, which is the perimeter. So I'm actually going to get that 500 is equal to 2w plus L. Because w plus w plus L is the perimeter, and that's what we need our fence to add up to. All right, our area equation is just as easy. It's just w times L, width times length. All right, we're going to do the same thing as before, solve for a variable in the equation with only two variables. I'm going to solve for L. So L is equal to 500 minus 2w. Now I'm going to plug that in for L in the other equation, and I'm going to get area is equal to w times 500 minus 2w. All right, I'm going to distribute because why not? 500w minus 2w squared. Let's take a derivative. 2a, or dAdw is 500 minus 4w. And this is going to be a very nice problem. All we have to do is plug in 0, add the 4w to the other side, divide by 4, and voila, our answer. And now we just plug the 125 back into our other equation to find our w. So 500 minus 2 times 125, whoops, not 1.25. And we get that L is equal to 250. So these numbers kind of make sense because it's going to be these add up to that number. These are nice numbers. It's not always going to be nice. It kind of depends on how the situation works out and which sides you use. So it's worth it to go through the calculus to check your work and make sure that it matches your intuition. Because often in these maximizing problems, your work doesn't always match your intuition. So while some people may have guessed that this was the answer ahead of time, I don't think anybody guessed that this was the right answer, the square root of 3 1/3. So where was the intuition there? So there's more to thinking to these problems than meets the eye often. And I hope this video helps.